You're not being bad. You guys have just had a lot of energy. Okay, so this is slide 54, and this is going to wrap up our states of matter finally. So see why I separated this unit from the classification? It used to all be together, and it was like a marathon. Nothing. I did steal some old pencils from home, so pretty good. Maybe like keep a hold of it for longer than a period.
Keep it?
I mean, if you keep it and you keep using it, that's fine. If you want to leave it in here so you don't figure it out. So yeah, when this all used to be together, it was a lot. It's kind of a lot on its own. But it does have a lot of kind of other random things in it that are going to be things that we've already talked about and things that actually are to come still. And this thermal energy idea, this transfer of energy is something that's not really going away. And so we're going to take a look at what this has to do with volume. So when you add thermal energy to a solid, a liquid, or a gas, the volume typically is going to increase. Think about it. We said that as you heat something up, the space between molecules will increase, right? And so if the space is increasing, that's what volume is. Volume is how much space something is taking up. So if your Chromebooks are open and you're filling in notes, that's fine. If they're open and you are not filling in, maybe just like so that you're not distracted. I know I can't compete with the internet or whatever you may be looking at. So if you're doing the notes, that's fine, but I better see you writing your notes with it. Okay, and again, we know that this is caused because as temperature goes up, kinetic goes up, and that's what the up arrows mean here. And so with more kinetic energy, the particles are moving more and more. They have more space between them, and this is causing the space that they're occupying to go up, which means that the volume is going up. It's not really new information, right? It's just kind of looking at it a little bit more specifically. All right, and so what do you think would happen to the volume if kinetic energy and temperature go down? What would be the logical reaction for that volume? What do you think, Dane?
It'll go down.
Thank you. I mean, I can wait you out. I mean, I really can. Volume would also decrease. Logically makes sense. And again, if the increase, because the space increased between the molecules, it makes sense that if the space goes down between the molecules, that's what would cause the volume to decrease. And it does. The particles are moving less and less, which is kinetic energy going down, meaning you have less space between them. And that less space that they're occupying means that there's less volume. Okay, and so if you think back to density, density is mass divided by volume, and you guys did so good with this unit. And so we have the equation m divided by v. So if we're heating or cooling something, the mass of the particles are not going to change, but the volume might go up or down. So we're not changing how much of the substance, and we're not changing the mass of it. It's just how much space is it taking up. So heating and cooling can affect something's density as well, because it's affecting volume. So any adjustment to volume would cause an adjustment or change in the density. And again, density is just how tightly packed are the molecules in a given amount of space. And so here, not nearly as dense as our solids, which is why typically solids are going to sink. We know that water is that weird oddball, that weird molecule because of the hydrogen bonds that form. They kind of like form in like that snowflake pattern, leaving that center area open. But most things, as they become solid, will become more dense. Right? And so we know, and this is going to be a good review because we're going to kind of come back to this here in the next couple units. We're going to see some more graphs where the equation matches the variables in the graph. And so just like with density, where we had mass and volume graph, the slope can tell us the density. And so this is going to be just kind of a nice refresher before we add in some new variables and new equations as we get into motion. But as you rise and then you run, right, the rise is our mass, the run is our volume, which matches our density equation, which is why a mass versus volume graph, the slope of the line gave us density. The variables on the labels of the graph match the variables of our equation, right? So here was our mass in grams, and here was our volume. And is this going to be a solid or a liquid? Does anybody remember? What do you think, Nevaeh? How do you know?
Because it's centimeter cubed and not milliliters.
Good. There's no version of the liter. So to be a liquid, you have to have some version of the liter. Good. All right. And so anything that has mass on our y-axis and volume on our x-axis matches our variables of rise over run, which also matches our variables of mass divided by volume for density, making the slope of this line represent density if I have mass and I have volume. Now, what would this represent? Is this going to be something that is a liquid or something that is a solid? What do you think, Kenna? Okay, how do you know? What do you see that tells you that? I like the oh wait.
No, liquid, because it says milliliters.
Nice save. Very nice. And so a lot of times it is easy, like if you're not sure and I put you on the spot, and even like when you're answering a question, you're like, I don't know, like you just click on something or you just say something, and it's like, if you just take a second, like it hit you, like something feels wrong. That's awesome, right? Don't ignore that feeling. A lot of times people get that feeling and then they just let it go. And so that's not okay, right? If you get the feeling, pay attention to it. It's kind of an alarm going off. Yes. Who do you need?
Layla.
Layla's the chosen one. All right. So we're going to see, it's disappointing. All right. I used to do this lab. We tried it for 2 years, and the first year it worked awesome because it was like negative 20 degrees outside. It was so cold. Like we were here, but it was really, 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 really cold. And so we could have an extreme difference in temperature, and it was easy. Like I could just take this balloon in this little crate and put it outside the door, leave it there, let the balloon get nice and cold, bring it back and measure it again really quickly. The next year we did it, it was still cold. It was like 15, 20 degrees out, and I thought that was cold enough, and it was not. I don't have a freezer that's close by. Like, I mean, I can have access to one down in the cafeteria or even the teacher's lounge, but it's still too far away. We tried a third year to put the balloon in the freezer, and by the time the balloon got back down here and we measured the volume of the balloon, the results weren't accurate again. So I found a video, and they can simulate it better. And like I said, the temperature, the weather has to be just perfect for it to work for us. It was fun to do. Like I wish that we could do it, but definitely the temperature today would not be good. It wouldn't give us good results, and it'd just be kind of a waste of time. So don't want to waste time. So we're going to take a look at this video that's going to kind of show this process.